Welcome back to our course on mechanical behavior of materials part 2. So in the last lecture, we discussed about ductile fraction mechanisms, and I talked about the mechanism in terms of void nucleation, growth, and coalescence, right? So we'll discuss a little bit more about ductile fracture mechanisms, including tunneling today, and then we'll complete this topic of ductile fracture mechanism. Okay. So let's proceed. So we now understand that inclusions, they play a very important role in ductile fracture, right? So if I plot strain versus FV, where FV is your volume fraction of inclusions, right? The plot is going to look something like this. So this is a schematic. This shows that if you increase the volume fraction of inclusions, then strain to fracture is going to decrease. So this is strain to failure. Okay. So increasing FV will decrease strain to failure. So, and in this case, suppose I take two cases where FVB is greater than FVA, where A and 2 are two different specimens having different volume fraction of inclusions. So FVBA is greater than FVA, and in this case, this plot is valid when we have constant size of inclusions. Right? So now let me draw two samples, A and B. Suppose we have specimen A and specimen B. Now the inclusion size remains same in both the cases, only changes the volume fraction of inclusions, right? So I am just making, say, size of the inclusions like this, okay? And in another case, volume fraction is increasing. Okay? And size remains same. So approximately I am drawing the same diameter of the circle, right? So these are your inclusions, right? Now, when you have when you do tensile loading, what is going to happen? The first step is we have discussed the void is going to nucleate, right? So void nucleated, and then they are going to grow. Okay. Suppose something like this. So all these remember these are schematics for understanding. Okay. So if you see in A and in B, voids have been nucleated, and the distance between the voids in B is much smaller than the distance between A, right? So the coalescence becomes much easier in B or much earlier in B, right? That means if we increase the volume fraction of inclusions, the distance between the voids is going to decrease, and therefore coalescence is going to become easier, which will lead to decreasing strain to fracture, right? So this is the overall concept of how you can correlate with the volume fraction of inclusions with the strain to failure. So higher the volume fraction of inclusions. Remember, we have also discussed about second phase particles, right? So I'm interchanging the term. You're going to have more number of voids, okay? And then this is the case void link up, okay? Or say coalescence becomes easier. And if this happens, strain to failure decreases. Right? And more number of voids are forming because you have more volume of fraction of inclusions, and this void link up become easier, right? Because spacing between the voids is small. Okay. So in B, it becomes easier for void link up. Okay. So strain to failure is going to decrease. So this is the case when you have constant size of inclusions. Now let's understand what happens when you have constant uh, volume of inclusions, but size is changing. So volume fraction of inclusions equal to same. Okay. Size is different. Okay. So now let's again consider two specimen. So say we have specimen A. Both are having same thickness. So gauge length, if we are talking about the uniaxial tensile test, the gauge length remains same for both A and B. Okay. Or gauge dimensions. Okay. So let me say that, initial length, I'm just assuming it to be L0 for both the cases, and they are same. This is specimen B, specimen A. Now I'm going to distribute the inclusion. So in A, you have more number of inclusions, but they are smaller size. In B, you have bigger size. And if you see, approximately, I am saying that the volume fraction of A is going to be equal to B. So here, size of inclusions in A is smaller than size of inclusions in B. Okay. And volume fraction is same. Now we are applying load. It's a uniaxial tension. So void is going to form. So I'm drawing both the specimens again, and then you have these inclusions. Okay. Now voids are going to form. So let me form the voids. Okay. So these are your voids. The purple color and the blue ones are your inclusions. Okay, now if you see in A, the distance between the particles is smaller, and therefore after the void has been created, the distance between the void is also smaller as compared to what you observe in sample B, right? So if I draw, after fracture, what happens? You're going to see something like this. So now we are in vision after fracture. You're doing uniaxial tensile test. You have formed the voids, they are growing, they are going to coalescence, right? And finally, you are going to see fracture happening. So in the case one, you are going to also, what is, these are going to link, right? So you are going to observe, say approximately something like this. And then your sample length is obviously going to increase slightly from the initial length, right? So this is say A. Now if I draw B, so here you are going to see again link up between these two voids, they will be link up. But since the distance between both the voids are larger, the link up is going to be delayed, right? And there will be larger voids also. Okay. So remember here, the size is smaller, the void size, the voids, number of voids are going to be larger, they are going to grow and they are going to link up, right? So after they link up, they are going to form dimples, isn't it? We have discussed this in the last lecture. So the dimple size here, whatever is forming, this is going to be smaller. Smaller than dimple size in B, right? This is one important concept what you can observe from the schematic I have shown here. Okay, so dimple size is going to be smaller. Dimples, number of dimples is going to be larger because number of voids are larger, right? So these are the two concepts. Okay. Now let me draw what happens in the case B. So you are going to have like something like this. Now if my original length was L naught, let's show here. So this was say original length. So in A, you see that the length has increased, right? Because you are doing tensile testing, the material is ductile, length is going to increase. But in B, you are going to observe higher length, right? Because of the concept I have just discussed. You see the schematic on the left side and it will be very clear, right? In A, the number of voids are larger, the distance between the voids are also smaller, so void link up or coalescence becomes easier. So you don't get much time, right, to increase the length before the coalescence as compared to B. So in B, you have more growth as compared to A. Okay. So if you understand the schematic, you can conclude that the dimple sizing A is going to be smaller than dimple sizing B. Number of dimples, if you observe the fracture surface, right? The number of dimples in A is going to be larger than the number of dimples in B. And finally, the strain in B is going to be higher than the strain to failure in A. So now let me write down, if I say this is 1, the second conclusion I can draw using this schematic is number of dimples will be higher in A Okay, because number of inclusions are higher, and that means number of voids are going to be higher. And the last one is number 3, strain to failure is higher for sample B than sample A. Okay. So now we have understood the effect of inclusion size as well as volume fraction. If you keep the size constant and if you increase the volume fraction, the distance between the voids is going to be smaller. That means strain to failure is going to be also smaller. Okay. Now, if you increase the volume fraction, increase the size of the inclusions, keeping the volume fraction same, the distance between the voids is going to be larger, which is the case B here right now. Okay. And that means the strain to failure is also going to be higher. Okay. So this is what I wanted to discuss about the effect of inclusion size and volume. Now let's understand, why do you get cup and cone failure when you do uniaxial tension? So cup and cone in uniaxial tension. Okay. So you are doing tensile test. So let's see, we have taken say dot bone specimen. And you're doing tensile loading. Okay. Now we'll again focus only on the gate session. So whatever I'm going to show you now, the schematics, those will be related to gate session only. Okay. So during tensile loading, if you plot engineering stress, engineering strain curve, initially you see elastic regime and then it goes to plastic regime, right? And about at the maximum load, you are going to see naked, right? So now let's make neck here. So now I am again drawing only the this session. Okay. So we have formed a neck, and this is the magnified version. So you can see very big neck. Okay. So you have now observed neck. Now what will happen? You are going to see the voids nucleation here. So you have taken commercial alloys, you have number of inclusions or second phase particle, you are doing uniaxial tensile test, voids are going to nucleate, right? We have discussed that at the locations of second phase particles. So these voids now are going to grow and they are going to coalesce. So you are going to form a cavity, something like this. Let me draw the sample. Okay. So this is cavity now. You have formed a cavity. Okay. After these voids have coalescence, right? So coalescence of voids to form a cavity or say crack. Okay. Now if you see what is happening here, you now are left with a very thin region. Okay. That is point one. Second, you need to also realize that when you have neck region here, okay, let's say I mark it number 1 and number 2 stage. So in stage 1, you have the necking, right? So this is acting like a notch, right? Now, if you remember the concept of line of forces or stress trajectory, the imaginary ones we discussed, you are going to observe the stress concentration in front of this neck, right? So you are going to see the stress concentration in these regions. Okay, and as soon as you have a stress concentration, you know that you are going to have triaxiality, isn't it? So as soon as the neck forms, the sample is no longer in uniaxial mode, it is in triaxial mode. Okay, so in the neck region, you have triaxiality. So here you also have triaxiality. Okay, and we also know whenever you have triaxiality, the void nucleation becomes easier. We have discussed that in the last lecture. Okay, so now we come to stage 2. These voids have formed. There is a triaxiality there, and they are going to form now a cavity or a crack. Okay, and now we are left with the region which is very, very thin, and for all practical purpose, in the region is thin, we can assume that they are in plane stress condition. Okay, before that it was in plane strain condition because of the triaxiality, right? So now this thin region here, we can say that these are in plane stress condition. So we have now left with thin section. They are in plane stress condition. Okay. Now, if you remember, when we apply Tresta criteria, this will be in biaxial mode now, right? Biaxial mode, because the sigma 3 is going to be 0, right? Now you apply, now you apply the Tresta criteria, and the yielding in plane stress is similar to the yielding in uniaxial tensile loading. Okay, remember that, because sigma 3 becomes equal to 0, so sigma 1 becomes equal to sigma naught. So that is similar to the uniaxial tension. This was also discussed when we discussed about triaxiality in front of the notch. Okay. So now the condition becomes similar to uniaxial tension. Okay, so yielding. So what will happen now? Shear is going to occur at 45 degree, right? Remember, the maximum stress, shear stress is at 45 degree when you are in uniaxial tension, right? So you are going to observe shear at 45 degree, and this will lead to the formation of shear lip. Okay, so now we are at, say, stage 3, where you are going to form shear lip at the end. We have this sample having the neck. Okay, and then you also have a cavity or track here. Now the region, which is the thin region left, we are going to form a shear lip. Say something like this at 45 degree. Okay, so this purple one is shear lip. Okay, you're forming, and remember this, this dot bone sample is your cylindrical sample, right? So you have a cross section which is a circle, right? So you're going to see the shear lip like this in 360 angle, right? Now if you observe both the surfaces, you're going to see one acting as a cone and another acting as a cup. So now if I mark this as part A and this is part B of the sample after they are fractured, you see A is your cup and B is your cone, right? And if I draw the sample for A, is going to look something like this. Okay, so this is your A, and you can see now this is like cup. Okay, it's like cup, and this is what I meant before as shear lip. So these two sections here. Let me change the color. So these two sections are your shear lip. Okay, and if I draw B, so B is going to be like this. Then you are going to have shear lip and then fibrous zoom like this. Okay. So shear lip. So these two are your shear lip. And this is like a cone. Okay, it's like a cone. So this is sample B and it's a cone. Okay, so this is how you form cup and cone when you do uniaxial tension. And remember, this is for commercial alloys and metals, right? You have to form voids, and then they are going to coalesce, they are going to link up and form track at the center, and then you are going to be left with a small thin section. They are going to form shear lip at about 45 degree. Okay, 45 degree angle. So now if you talk about the dimples characteristic in the center region as well as shear lip. So the center region typically we call it as fibrous zone. Okay, and the corner one it is shear lip. Okay, so if I just see the surface, suppose this was my sample and this was the center zone and this is your shear lip. Now you are imagining in 3D. Okay, so this is the flat zone. If you see in 3 dimension, your sample is cylindrical. So this is your, say, flat zone. Okay, or we call it fibrous zone. And the other one, this guy here, this is your shear lip, about 45 degrees. So it's inclined, right? Now, if you see the dimple characteristics, so in shear lip, you are going to have dimples which are elongated. Okay, and in the fibrous zone or flat zone, you are going to have dimples which are equiesced. Okay, so in cup and cone failure, if you observe the fracture surface, you are going to see at the center, which is almost flat, it will be fibrous zone or flat zone, where you will see the dimples which will be equiesced. And if you remember, each dimple is going to also contain inclusions, right? Now, if you see the shear lip, then your dimples are going to be elongated. So now if I just write down, you have, say, two part A and B. So you are doing tensile testing. So you have fractured the sample. So you are going to have part A and part B. Okay, so let me draw two cases. One will be for shear lip, another one is for fibrous zone. Okay, so in shear lip, you are going to see dimples like this on both the surfaces. Okay, and in fibrous zone, you are going to see dimples elongated, right? And it is going to change in both the surfaces because it's a shear. right? So in one surface, it is going to look something like this. In another one, it is going to be in the opposite direction. Okay, so this is your fibrous zone, shear lip. Okay, so now let me summarize under tensile loading. Okay, second is they grow out of the plane. So these, voids, they are going to grow out of the plane. Third is you are going to form equiesced dimples. And fourth, as I mentioned already, this is fibrous zone of cup and cone failure. Okay, so this corresponds to this. Now the second one, under predominantly shear loading. So shear lip is forming because of shear loading, right? So they coalescence, the voids, they are going to coalescence along plane of maximum shear, which is 45 degree. Okay. So this leads to elongated dimples. And this is happening in shear wall or shear lip of cup and cone fracture. Okay. So when you do tensile loading, you're going to see different dimples characteristic if you are in fibrous zone and if you are in shear lip. Okay. And this is what you observe typically when you have commercial alloys or commercial metals. Okay. Now let's understand the concept of something called tunneling, and it happens when you already have a crack. So what happens when crack is already present? And we'll utilize this concept to understand, the effect of thickness on fracture toughness. So when I was teaching fracture toughness, you remember, I told you at that time that we are going to talk about fracture mechanisms, and there I will also discuss about one of the reasons why the fracture toughness decreases with increase in the thickness. Okay. Okay, so you have a crack, and we are talking about commercial metals and alloys. You are going to have the inclusions, right? So you have a track, and this track is seeing inclusions in front of it, right? We also know that the stress is going to be higher, right? Because of stress concentration in front of the crack tip. So what is going to happen? You are going to nucleate voids, right? At the locations of inclusions, either by debonding or by the fracture. We have discussed about that concept, right? And finally, they are going to merge and or coalescence, and this track is going to grow like that. Okay. So you're going to now have nucleation of crack, and they are going to grow. So in the next step is a, let me now draw all the inclusions. Okay. And then you have the same crack here, right? So you're going to now nucleate, and then they are going to grow. This will lead to something like this. Say for void 1, void 2 are like this. Okay, so this is like nucleation and then growth. So you have formed the void, they are going to grow, and the void which is very near to the track, they are going to merge with the track, and this is how your track is going to propagate. Okay. So you have initiation, growth, and coalescence. At the tip of a pre-existing track. So what is going to happen locally? Void will nucleate. Okay, because stresses are higher at in front of the track tip. Okay, so you are going to see void nucleation, and remember, because it is in triaxial mode also, because of the stress concentration, void nucleation becomes much easier when you have a presence of crack. Okay? So locally void is going to nucleate, they are going to grow and link up with the main crack. Okay, and this is how your track is going to propagate when you have ductile or say commercial metals and alloys where you have presence of inclusions. Okay, so this is how the track is going to propagate, track propagation. Now, if you remember, we had discussed this, that if you have a track along the thickness, the triaxiality is going to vary, right? And you remember this plot. So if this is b by 2, this is 0. So we are talking about distance from the center along the thickness. Distance from the center. So b by 2 is half of the thickness of the specimen, right? So this is high triaxiality. So this was in plane strain. And here at the surface, you have plane stress. So we have discussed this while we are discussing about plastic zone size. Just go through the lecture. Okay. Now, if we have a sample, which is say B thickness, inside the sample, you are going to have triaxiality, and on the surfaces, you are going to have plane stress. So inside you have plane strain, and on the surfaces, you are going to have plane stress. We now know also that whenever you have plane strain condition or high triaxiality, the void nucleation and growth becomes much easier, right? So if you have a track, pre-existing track, the void is going to nucleate, and the growth also, it will be much easier inside the sample as compared to the surface. So what will happen? Your track is going to grow much faster inside the sample as compared to the surface. Okay, because of triaxiality inside the sample. Okay, so what I am saying that due to triaxiality, at the interior of the sample, or say plate, void nucleation and growth becomes easier inside the plate as compared to the surface. Okay, and if this happens since the void nucleation and growth has now have now become easier, right? The merging of these voids with the main crack becomes also faster, right? So the crack growth at the center becomes higher. So you see faster crack growth at the center, and this is what we call as tunneling effect. And the remaining ligament, I will show you the schematic. I will draw it. Okay, they are going to form shear lip. Okay, so now let me draw the schematic. So what I'm saying that suppose you already have a track. Let's something like this. So you have a track and say the sample, the track front is same throughout the thickness. Okay. So what will happen? You have lots of inclusions in front of the track. So they're going to grow and they're going to merge with the main track as we discussed, right? Now this process is much faster in the central region as compared to the surface because of the triaxiality inside the sample, right? So you're going to end up getting a track front profile at a certain amount of time that will be something like this. Okay, so say this is your sample surface here. Imagine that is in 3D sample surfaces are there, and inside the sample you are going to see a track profile like this. Okay, so this is your track profile. So this is your track now. Okay, and it's happening, and this is what is called tunneling effect. You are actually making a tunnel, right? Now use the same concept we discussed before with respect to shear leg during cup and cone, right? So now this ligament, whatever is left here, this ligament here in the green, right? So they are now under plane stress because it's a very, very thin region which are left after the crack has grown faster inside the sample. So these two are now under plane stress. What will happen if it is under plane stress? Now correlate with your cup and cone failure, you are going to form shear lip, right? So inside you have a flat surface and then you are going to form shear lip at the corner. So now if you draw the 3D profile, you are going to see something like this. Now let me try to draw the schematic. Hopefully something like this. Okay. So now if you see, you are going to have a track here. So this is your track, or this is after fracture. Huh? You have fractured the sample. So these two are your shear lip. This point also, okay, shear lip. Ideally, it should be something like this, I'd say. Right? And this is your interior, which is under plane strain condition. So I'm looking from this side. So your track was initially this side. Okay, and track is drawing. So this is your track propagation path or direction. Okay, so your track is going to propagate along that direction. You form a shear lip, and inside your track front is higher. Okay, so this is top view, I would say. If you see from the top, it is going to look the track profile like that, and this is 3D view. Okay, so this whole thing is called tunneling effect. Now, if you draw, what happens when you vary the thickness? Okay, so if I draw, suppose I have very thin sample, right? That the whole sample is say under plane stress condition, plane stress. So it is going to have a shear lip directly, right? So this is very thin sample. Okay. Now, if I increase the thickness, you are going to observe what we have discussed just now. So see on the 3D view, if you see from the front, you are going to observe a section like this. So you are seeing now the front view. Okay, so you are looking this side. So your eye is here. So you are looking like this. Okay, so this is your shear lip or slant surface, a slant face. Okay, here also you have these two slant face. Okay, and this one is your flat one, flat surface. And if I increase more and more, you are going to end up having a situation like this. So remember, this will be under only plane strain condition when the ligament is thin, right? So your ligament size at the end is going to be smaller. So only the small fraction, if you increase the thickness, only the small fraction is going to form shear lip. Okay. So this is your again slant face. Okay. And what we are doing, we are increasing the thickness. Okay, so if it is very thin, it will be say 100% shear lip. If it is very thick, okay, so most of the sample is under plane stress and plane strain condition. So you are going to observe flat region, and at the end, right, which is under plane strain condition, due to the tunneling effect, you are going to see shear lip. And at the intermediate region, you are going to have effect from both plane stress and plane strain condition. Okay, so this is how your fracture surface is going to look like when you already have a crack and when you increase the thickness. Right now, let's correlate this quickly with your fracture toughness we have discussed. So if you remember, Your variation of fracture toughness was something like this. So Kc, and here is your K1C. And we were increasing the thickness. Okay. And at that time I mentioned that if you increase the thickness after a critical thickness, Kc will become equal to K1C, which is plane strain fracture toughness. So this is plane strain fracture toughness. And we have also discussed about the standard for measurement of fracture toughness, plane strain fracture toughness, and we know that the thickness has to be sufficient so that the criteria, if you remember, should be satisfied, right? Now utilize the same concept, this one, to understand what is happening here, right? So if you have very, very high thicker material, right, it is predominantly under plane strain condition. If it is very, very thin, it is predominantly under the plane stress condition, right? So the effect is in that sense here that the thickness effect on the fracture toughness is due to the relative proportion of the flat and slant surfaces. Okay, so let me write down. The thickness effect on the fracture toughness is due to the relative proportions of flat and slant surfaces, right? Or flat, and you will see in many books shear fractures. Slant surfaces will be called as shear fracture. Okay, so you are going to have flat fracture region and then shear fracture, which is the slant surface. So depending upon the relative proportion, you are going to see that effect on the fracture toughness. Okay? So after a particular thickness, the contribution from flat fracture has high dominance and further increase in thickness does not change the fracture toughness. Okay, so let's understand what I just wrote. Let me go back to the image here. Okay, so when you increase the thickness, the proportion of the flat fracture is going to be increasing, right? There it is going to increase. So after certain thickness, what is going to happen? The dominance of the flat surface, if you see the area fraction, if you see the fracture surface and you say, okay, this is the area fraction of flat surface and this is the area fraction of slant surface, the dominance will be very high, or in fact you can neglect the effect of slant surfaces or slant faces after certain thickness, right? And when that happens, if you increase the thickness more and more, there will be no effect on the fracture toughness. Okay, and if that thickness, let's say, is a critical thickness, below that there will be some effect of the slant surfaces. Okay, so this is how we correlate the tunneling effect with the fracture toughness. That means that the relative proportion of the slant face as well as the flat surfaces with respect to thickness, and that we can correlate with the fracture toughness. Okay, so we have completed today the ductile fracture mechanisms. In the next lecture, we will quickly talk about some concepts of brittle fracture mechanisms. Thank you.